All right, let's dive right in. Have you ever really stopped to think about what's going on inside a battery? Well, today we're going to build one from the ground up, piece by piece, so we can really understand the engine at its core, the galvanic cell. But first, let's start with a feeling I bet a few of us know all too well. Have you ever been chewing gum, maybe bit down on a piece of the foil wrapper by mistake, and felt that weird, zappy jolt in your mouth? Especially if you have fillings? Yeah, that zap? That is actually a tiny, uncontrolled electric current. It's a spontaneous chemical reaction happening between the aluminum foil and the metal in your dental work, with your saliva acting as the conductor. Believe it or not, you've just created a very, very small battery right there in your mouth. And that little shock is the perfect place for us to start, because it's a real-world example of the big idea we're exploring today, how you can take chemical energy and turn it into useful electrical energy. So that zap in your mouth is just raw, untamed energy. To figure out how we can actually harness that power, we first need to look at a classic chemical reaction where all that potential just kind of goes to waste. Okay, so picture this. You take a strip of zinc metal and you drop it into a beaker of copper sulfate solution. It's this really bright blue liquid. The moment they touch, bam, a reaction kicks off instantly. Electrons literally jump directly from the zinc atoms over to the copper ions in the solution. So what's actually happening on a molecular level? Well, the zinc is getting oxidized, which is just a fancy way of saying it's losing electrons. At the exact same time, the copper ions are getting reduced, meaning they're gaining those same electrons. Now, this transfer of electrons is powerful for sure, but because the chemicals are touching, all that energy just escapes as heat. So, that's our challenge. How do we intercept those electrons and make them travel along a path where they can do something useful for us? All right, so the logical first step seems pretty simple. Just separate the two chemicals. But as we're about to see, this easy solution creates a brand new and very unexpected problem. So let's try it. Imagine two separate beakers. In one, we'll put our zinc strip in a zinc solution. In the other beaker, a copper strip in its own copper solution. Then, we connect the two metal strips with a wire. The whole idea here is that now the electrons are forced to travel through that wire to get from the zinc to the copper. And for a split second, it works. A meter would show a little flicker of current, but then almost immediately, nothing. The flow just stops dead. So, what happened? What are we missing here? Okay, here's the issue. It's a traffic jam of electric charge. In the zinc beaker, as the metal strip loses its negative electrons, it's dumping positive zinc ions into the liquid, so you get a buildup of positive charge. Meanwhile, over in the copper beaker, as positive copper ions stick to the metal strip, they leave behind all their negative partners. So that solution builds up a negative charge. In an instant, the whole system short-circuits itself. The positive side won't let go of any more negative electrons, and the negative side won't accept any. The circuit is broken. So, how do we fix this charge problem? Well, the solution is an incredibly clever and absolutely essential piece of the puzzle, known as the salt bridge. A salt bridge is pretty much exactly what it sounds like. It's just a U-shaped tube filled with a salt solution and electrolyte that won't interfere with our main reaction. We stick one end in each beaker, connecting the two liquids. The salt bridge's entire job is to keep things electrically balanced. It's like a traffic controller for ions. As that positive charge starts to build up in the first beaker, negative ions flow out of the bridge to cancel it out. And as negative charge builds up in the other beaker, positive ions flow in from the bridge to balance that. This simple little fix keeps both sides neutral and allows the electrons to keep flowing through the wire. The circuit is complete. So now that we have all the pieces on the board, the two half cells, the wire, and our hero, the salt bridge, we can finally look at the whole system and give all the parts their proper names. This whole setup, this is what's officially called a galvanic cell. It's a device that takes a spontaneous chemical reaction and uses it to generate an electric current. And in its most basic form, this is a battery. Okay, so each of those metal strips is called an electrode. The electrode where oxidation happens, our zinc strip that's losing electrons, is called the anode. Since it's the source of electrons, it's the negative terminal. And the electrode where reduction happens, the copper that's gaining electrons, is the cathode. It's the destination for those electrons, which makes it the positive terminal. And what's really cool is that you can actually see this happening. If you let this cell run for a while, you'd watch the zinc anode literally get smaller as it dissolves into the solution. At the same time, the copper cathode would get heavier as new copper atoms plate onto it. Even the blue color of the copper solution would start to fade as those copper ions are used up. And of course, your voltmeter would confirm the whole time that, yep, Electrons are flowing from the zinc to the copper. Now, as you can imagine, chemists really didn't want to draw this entire setup every single time they needed to describe a cell. So naturally, they came up with a really clever shorthand for it. It's called line notation, and it's awesome. It lets us represent that entire complex setup of a galvanic cell in just a single, standardized line of text. And for the zinc-copper cell we've been building this whole time, this is what it looks like. Now, I know, at first glance, it might just seem like a random string of symbols, but I promise, it's actually incredibly logical. Here's the secret to reading it. The rule is simple. Anode on the left, cathode on the right, always. So on the far left, you've got your solid zinc anode, separated by a single line from the zinc ions it's making. That single line just means they're in different phases, solid and liquid. Then, in the middle, you've got that double vertical line. That's the universal symbol for the salt bridge. And then on the right side, you've got the cathode half cell. See? It's basically a little map of the entire battery. So let's just quickly recap the big ideas here. A galvanic cell makes electricity by splitting a chemical reaction into two separate half cells. This forces the electrons to travel through an external wire, going from the anode to the cathode, which creates a current we can use. And the whole thing absolutely cannot work without that crucial salt bridge, which keeps the charges balanced and the electrons flowing. So now you understand the fundamental blueprint of a battery. But this brings up one last fascinating question. We saw that zinc gave its electrons to copper. But why? Why didn't it happen the other way around? What decides which metal wins what the source material perfectly describes as the tug-of-war for electrons? Well, the answer to that question is the real secret to creating all the different kinds of batteries that power our world today.